Good afternoon. Welcome to week 8 of the NPTEL course on applied optics. This week we have been focusing on Fraunhofer diffraction. We saw diffraction from a rectangular slit, from a circular aperture, and also diffraction from diffraction gratings, and how gratings work, what are the different terms, for example resolving power of a grating, and these were the terms that we focused. Finally, we had also introduced the concept of Fresnel diffraction, and in the next week, in week 9, we will be focusing on Fresnel diffraction. So this week has been on Fraunhofer diffraction from different kinds of apertures. So let us get started with the first question. So this question is on diffraction grating. A very simple question. It just asks you what exactly is a diffraction grating. So a diffraction grating is a single slit, B, repetitive array of either aperture or obstacles, C, double slit, or D, none of these. So very simple question. Take about a minute. Let me launch the poll. Yeah. Okay, so let us now discuss the answer. The correct option is repetitive array of aperture and obstacles. So diffraction grating, what exactly is it? It's like multiple slits. So you have an array of these multiple slits very closely spaced. So let's say this is a slit, then this is obstacle, then a slit, then obstacle, then a slit again, and so on and so forth. So many such apertures and obstacles are there. So that is what is a diffraction grating. For example, a typical diffraction grating could have something like 10,000 lines per inch. So, for example, of the order of 10,000 lines per inch. This is, let's say, the typical order of a diffraction grating that is commercially available and you can purchase. You could also have, let's say, from about 1,000 to 10,000 or 15,000 even. So this is the order that we are talking about. So 20,000, 10,000, 1,000. So in this scale, it is not like you would have, let's say, 10 lines per inch. No, that is not happening. And also it's not as if you would get like 1 lakh lines per inch. No. So this is the kind of order, like thousands to 10,000s range. Okay, so let us move to the next question. Oh, where is my pen? The radius of the first dark ring produced from aperture diameter d with focal length f is what we need to select. A 1.22 f lambda by d, 1.22 f d by lambda, 1.22 d lambda over f, and d 1.22 d over f lambda. And lambda is wavelength. Of light. So we need to select the correct option. Take about a minute or two to answer this question, and then we will discuss. Okay, let me restart the poll. Yeah, there you go. In the meantime, for those of you who have joined late, I will put the link to the YouTube channel for this course in the Zoom chat box. So this YouTube channel is where you would find the recordings of all the previous sessions, as well as this particular session would also be live streamed over there. So if you happen to miss any session, or if you face some network issues in Zoom, sometimes Zoom does funny things and the screen becomes blurred or the audio is not clear. So in those situations, you could head over to the YouTube channel and watch the live stream over there. Okay, so let us now discuss the answer. For this purpose, we need to study the diffraction effect from a circular aperture. So, diffraction by circular aperture. Okay, so here is my circular aperture. Let's call this Y, this Z. And then the screen is placed at some distance. And I'm looking at some point R on the screen, which makes an angle theta from the horizontal. Okay, so this is the setup. And now we need to look at the electric field. So first of all, before starting, you could immediately see that option D is dimensionally incorrect. So we can just simply rule out option D. And why is it dimensionally incorrect? Because you want to find out radius. Radius would have a dimension of length, whereas D over F lambda would have a dimension of 1 over length. So let us now write down the electric field. So this is the diffraction integral that I am writing. This ds is the area and this integral is to be performed over the aperture. Now we can look at the transverse plane. So if I look at the transverse plane, then I have this circular aperture over here. These are the axes passing right through the middle. And So let's say this is some point over here. This angle is phi. Okay, I think this is becoming too tiny. Maybe I need to zoom in. Maybe I need to reduce the thickness of my pen. This angle is phi, this distance is rho, and this radius is a. Better. Yeah, so this is the transverse plane for the aperture. Similarly, the transverse plane for the screen. This is the screen. And again, I'm looking at some point which is at a distance, say Q, and at an angle capital phi. Okay, then from these we know that Z is rho cos phi, because this is Z, this is Y, this is capital Z, this is capital Y, and Y is rho sin phi. Similarly, capital Z is Q cos capital phi, and capital Y is Q sin capital phi. Also, this area element ds is rho d phi. This we know from polar coordinates. So with these, the integral over the aperture transforms into a rho integral over the radius and a phi integral over the angle. And also the term y plus z becomes the following. And using the trigonometric identities, this would reduce to the following. Okay, great. Now we can proceed with our integration. So the electric field on the screen would be given by the following. Now we see that there is axial symmetry, means radial symmetry is there. Along the angle there is a symmetry. So because of this, what we can do is, because of the axial symmetry, the aperture is axially symmetric. Because of this axial symmetry that we have, we can set capital phi equals 0 and study only that particular direction without any loss of generality, because no matter what my value of capital phi would be, the distribution would be the same because of this axial symmetry. So I could be taking a 1D cut along any phi direction and the pattern would look the same because of the symmetry of this problem. Okay, so let us now proceed. From special functions, we know that the Bessel function of first kind is given as follows. Which for m equal to 0 becomes the 0th order. So for m equals 0, this reduces to and also some recurrence relations are there for these Bessel functions. So we have some more relations which I would write down. So this is another relation. And again, if we were to set look at J0, so here if we put in m equals 1, we get the following. And this is just basic calculus, principle of calculus. Okay, so now using these identities, our electric field at the screen would become the following. For the angular integral, we would use this. And how we got this? Well, for our case, v was phi because we had set capital phi equals 0, and u was k rho q over r. So from these substitutions and using this identity, we have reduced this integral to this. Now we can make other substitutions. We can, let's say, make w equals k rho q over r. This gives me d rho equals r over k q dw, and when rho equals 0, then W equals 0. When rho equals A, W equals KAQ over R. So this integral would then become integral over W and now this integral, we can make use of this identity over here. Also there is a W also, sorry I forgot that. Yes, so now this would become using this identity. So putting everything together would give us the electric field at the screen. So this is the final expression for our electric field. Now intensity is given as proportional to mod E squared. So mod E squared is E star E. Stop me at any point if you are getting overwhelmed. It's just plain simple algebra at this point of time. So this part I can write as I naught. Rather I naught by 2 or 2 I naught, sorry. Oh, sorry, this is I naught and 2 is not inside the square. 2 is outside. Where sine theta is nothing but q over r. From here you see sine theta, and this is q, so sine theta would be q over r. So this is the expression for intensity. Now we also know from properties of Bessel function that J1U is 0 when U is 3.83. This is for the first 0. So the first 0 for Bessel function of the first kind of first order occurs at the location 3.83. So this first 0 is where you would see the first dark ring. The second 0, if you want to know, second 0 is at the location 7.02, and so on. Similarly, you would have third 0, fourth 0, and infinitely many zeros. So this implies U over here for me is KAQ over R. This is 0 when this is this J1 is 0 when this is equal to 3.83. So this gives me Q equals 3.83 R over KA. K is 2 pi by lambda A. So this comes out to be approximately 1.22 R lambda over 2A. Now in our case, 2A equals D, R equals F. So this is 1.22 lambda F over D. So the correct option is option A, 1.22 F lambda over D. And why? Because we keep the screen at focal length in Fraunhofer diffraction. So this was the entire maths for diffraction, Fraunhofer diffraction by a circular aperture. And let me highlight the final result. So this is my expression for the electric field, final electric field on the screen, and this is my expression for final intensity. And you see that the first dark ring occurs at this location 1.22 lambda F by D. And clearly from this you can see that if you decrease your D, then radius of central bright spot, or equivalently radius of first dark ring increases. That means if my aperture size decreases, then my diffraction pattern size increases, which is true because there is an inverse Fourier relation between the diffraction pattern and the aperture. Similarly, if my lambda increases, Then also I observe the same thing, that my radius of central bright spot or first dark ring will increase. And also if my focal length increases, then also the radius of central bright spot or the first dark ring will increase. So you can clearly see from this expression the effect of different parameters on the diffraction pattern. Okay, so that was pretty long for a single question. Let us now move ahead. Is there any question? Let me check the Zoom chat box and YouTube chat box. Oh, someone is asking why R equals F. This is because Fraunhofer diffraction regime is when we consider that the screen is at infinity. So the distance between the aperture and the screen should be infinite, and we can simulate that condition also by keeping the screen at the focal length of a lens. So after the aperture, we'll place lens, and the screen would be at the focal length of the lens. That also basically uh, imitates the situation of the screen being at infinity. So this is for Fraunhofer diffraction. For Fresnel diffraction, you won't have this. Okay, so I hope that answers. Fine, now we can proceed to the next question. Question number 3. Again, this is on circular aperture. A circular aperture of radius 0.01 centimeters is placed in front of a convex lens of focal length 25 centimeters and is illuminated by a parallel beam of light of wavelength 5 into 10 to the power minus 5 centimeters. The radius of the first ring is what we need to find. And these are the 4 options. Okay, so I will give you about a minute or two to answer. This is a very simple numerical question. It is based on the previous question that we just solved. Okay, so let us now discuss the answer. So this is pretty simple and straightforward numerical based on the previous question that we just solved. We will make use of this expression right here, and we have already been given lambda is 5 into 10 to the power minus 5 centimeters. Focal length is 25 centimeters. Radius A is 0.01 centimeters. And D is nothing but 2 times A, which is 0.02 centimeters. So the radius of the first ring, they mean the first dark ring, would be by this expression 1.22 lambda f over d. So 1.22 lambda is 5 into 10 to the power minus 5 centimeters. F is 25 centimeters and d is 0.02 centimeters. So let me pull out my calculator and plug in these values. Okay, wait, where is my calculator? So 1.22 into so this is equal to 76.25 into 10 to the power minus 3 centimeters, which is 0.7625 millimeters. So the correct option is option B. So this was a pretty simple, straightforward question. You would get such numericals as well in your assignment. So, and this is a very important result, this 1.22 lambda f by d for the radius of the first dark ring. This is a pretty important result and you should remember this. And the derivation is pretty complex, like you need to remember a lot of stuff, so it is better and easier to remember this simple relation. Okay, moving ahead. Question number 4. This is on Rayleigh's criteria. According to Rayleigh's criteria, to just resolve images of 2-point sources, one requires four options would be there. So we have basically 2-point sources and we want to see if we can resolve them. So each of the point sources would undergo diffraction circular aperture diffraction to be precise. Sorry, there was a spelling error. Okay, so this question is on Rayleigh's criterion, and these are the four options. Rayleigh's criterion basically tells us the condition when we can resolve 2-point sources or two different wavelengths. So let me refresh and relaunch the poll and take about a few minutes to answer this. Okay, so let us now discuss the answer. So first let me tell you the correct option and then we will discuss why it is correct. So the correct option is option A. According to Rayleigh's criterion, to just resolve images of 2-point sources, one requires the center of one airy disk pattern should fall on the first minimum of the airy pattern of the other point source. So let me try and draw the airy pattern. So for those of you who are confused, airy pattern is nothing but the diffraction pattern of a circular aperture. So this is also known as airy pattern. Okay, so and how does this pattern look like? Well, it is like circular regions. So this is like one bright spot, then there will be a dark ring, then there would be like a bright ring, like a bright ring again over here, and then a dark ring, and these rings, they would become thinner and thinner as we move away from the center. So this is how the airy pattern looks like. So let me draw the 1D cut of this over here. I will try my best to draw. Let me see how good I can do. Okay, wait. Let me. Okay, nice. Can I copy paste this? Copy. But I don't think I can possibly rotate this. No way. Fine. Okay, so this is probably my best attempt. This is for one source. Let me copy paste for the second source, change its color. Okay, so this is the situation when we will say that this is just resolvable when this maximum falls on this first minimum, like this. So this is the minimum, this is the minimum, and this is the maximum. So this is the least separation for resolving. And how much is this distance? We already know this is 1.22 lambda f over d. Of course, if the distance is more, then you are able to resolve very nicely. If the distance is less, then you are not able to resolve these sources. And how could I better increase my resolution? So in order to increase my resolution, I would have to increase the resolution, I would have to decrease my wavelength. And why? Because if I decrease my wavelength, then the least separation for being able to resolve would also decrease. That means if the two sources are placed very close to each other, then also I will be able to resolve them if I decrease my wavelength. So this is the concept which was this is like a basic concept for understanding why people came up with the electron microscope. So the traditional microscope uses optical light. So optical light would have wavelengths in a certain range, which is of the order of from 400. So optical wavelength is of the order of 400 to 700 nanometers. So this would offer you a certain resolution, but if you want to increase your resolution, you need to decrease the wavelength, and this can be provided if we use electrons as the probe. And so that's how people came up with the concept of electron microscope. And electrons have a wavelength of the order of picometers. And how we get this is from the de Broglie wavelength, which is given like this. P is the momentum, H is the Planck's constant. So if we decrease the wavelength, then we increase our resolution. Great. Now we can proceed further. To the fifth question. This is also on Rayleigh's criterion. The minimum resolvable angular separation is what we need to find out. I have restarted the poll. Take about a minute to answer. Okay, so let us now discuss the answer. So this is again based on the first question that we did. Over here we will make use of this very equation. So what we have is Q is 1.22 R lambda over 2A for the first ring, and this is also the distance required for least separation for resolving, as we saw in the previous question. So this is now sine theta. We need to find angular resolution. Sine theta is Q by R, which is 1.22 lambda over D, which is approximately theta for small angles. So the angular separation, minimum resolvable angular separation, is 1.22 lambda over D. So in this question we combined the concepts done in question 2 and question 4. So in question 2 we saw what is the radius of the first dark ring, and in question 4 we saw that that very same radius of the first dark ring is what is the least distance for being able to resolve two closely spaced point sources. And from that least distance we can find out the angular separation, the least angular separation as well. So pretty simple and straightforward. I hope there is no concern regarding this. Okay, someone is asking why I wrote sine theta is Q by R. Again, if you go to this question 2, you see from this this diagram over here, this is theta, this distance on the screen from the origin to the point R is Q, and okay, I did not write what is R. Okay, so this is the distance R. I think that was the confusion. I wrote this R over here, but it is this distance. This distance right here is what is R. Okay, so I hope that clarifies the question. Okay, good to see that people are asking questions. Okay, fine, so we can proceed now to the next question. We are halfway through. There are 10 questions, 5 questions done. Question number 6. This question now is on diffraction grating. This is the grating spectrum. The equation for the grating and the diffraction pattern observed from the grating. Okay, please answer this question and select the correct option in the poll that I have created for you. Okay, so let us now discuss the answer. So a diffraction grating, as we saw in the first question, is basically a collection of many slits. So if I were to write the equation, so what is a diffraction grating? It's basically many slits put together. And the intensity pattern for n slits we saw previously in the lecture notes, in the videos. If you see, you would find this expression for the diffraction pattern from n slits. Now here alpha is Ka sine theta by 2, beta is Kb sine theta by 2. A is the slit separation, B is the slit width, and N is the number of slits. Now, the principal maxima of this pattern occur when sine n alpha over sine alpha is maximum, and this is maximum for the following values of alpha. Alpha equals 0, plus minus pi, plus minus 2 pi, and so on and so forth. Integral multiples of pi. So that means alpha is m pi, where n is an integer. Now if we look at alpha going to 0, so limit alpha tending to 0, sine n alpha over sine alpha, we will make use of L'Hopital's rule and differentiate the numerator and denominator. So derivative of numerator is n cos n alpha. Derivative of denominator with respect to alpha is cos alpha. So now if we plug in alpha equals 0, we get L. And from here to here, this step to this step was by making use of L'Hopital's rule, which says that if you have a 0 by 0 form or infinity by infinity form and you want to find out the limit, then you differentiate the numerator separately and differentiate the denominator separately with respect to the variable in consideration, and then plug in the value to get the limit. So now we can put things together. So we have alpha equals Ka by 2 sine theta, and let's say this theta is for the principal maximum. So for principal maximum we have this value of alpha, so this is equal to m pi, which implies a sine theta m equals 2m pi over k. K is 2 pi by lambda, so 2m pi over 2 pi by lambda, which is nothing but m lambda. So we get a sine theta m equals m lambda. So that is the grating equation, the grating spectrum. I hope this is clear. So this was for normal incidence. And the question is, what happens when you have a non-normal incidence, when the laser light is not following normally on the grating, if it falls at some other angles, then what happens? This we would see for oblique incidence, one equation for oblique incidence as well. But for now, let me show you a video. So, okay, something happened. I had opened the video, but it's not visible. Okay, let me open. So, I have uploaded a video on my channel for grating spectrum when the incident light beam is not normal. Let me just figure out where is it. Yeah, here. So this is a video that I have uploaded on my channel, and this video basically demonstrates the diffraction pattern by a grating. So let's have a look at this video and see the diffraction pattern obtained.
A laser pointer and a grating. We have all performed undergrad optics experiments with these. So here's the diffraction pattern. An equidistant set of points.
So this is for a grating with normal incidence.
That's the case for normal incidence. What happens if we try tilting the grating sideways, left and right? So the points in one direction.
So this is now oblique incidence.
Away, whereas they come close together on the other side. Now tilting in the other direction.
So this is sideways tilting, meaning I am tilting the grating such that the incident angle is no more normal and it makes some angle theta. So when I mean sideways tilting, I mean the axis of rotation is passing through the grating and it is in the vertical direction. So it is about the vertical direction and not the horizontal direction. So if we rotate about the vertical direction, then that is what I call sideways tilting over here.
Same thing. Magic happens if we try tilting the grating up and down. So the points start forming an arc and finally a circle when the reflected and the transmitted spectra come together.
So this is where up down tilting, meaning tilting about the horizontal direction. And you can see very nice circular pattern of dots is obtained. And how this is happening? This is happening because a grating is not just a transmission grating. It transmits part of the light, it reflects part of the light. So the top half of the circle that you see is from the transmission spectrum, and the bottom half of the circle that you see is from the reflection spectrum. Okay, so let me play it once again for you.
A laser pointer and a grating. We have all performed undergrad optics experiments with these. So here's the diffraction pattern. An equidistant set of points. But this is just the case for normal incidence. What happens if we try tilting the grating sideways, left and right? So the points in one direction start moving away, whereas they come close together on the other side. Now tilting in the other direction. Same thing. Magic happens if we try tilting the grating up and down. So the points start forming an arc and finally a circle when the reflected and the transmitted spectra come together.
Okay, so that was it. Let's come back. Moving ahead. To the next question. Question number 7. I'm sorry, where's my pen? Yeah. Question number 7 says the resolving power in mth order spectrum of a grating is option A n over m, option B. Okay, before this I just want to point out one thing, that in the previous question option D was dimensionally incorrect. So dimensional analysis is very important. You would be able to rule out some of the wrong options in an MCQ question simply by dimensional analysis. So this is dimensionally incorrect because on the left hand side you have cos theta, which has no dimension, and on the right hand side you have m lambda, which has dimensions of lambda, the wavelength, which is the dimension of length. Okay, now that I've pointed that out, I'll come back to the current question number 7. Oh, sorry, I need to change the color of my pen. Okay, so once again, let me restart the poll. Please take about a minute to answer the question. Okay, so let us now discuss the answer. So I showed you the video for oblique incidence after the previous question, and here I will write down the equation. This is for sideways tilting. So oblique incidence for sideways tilting, in this case our alpha is not just Ka by 2 sine theta, instead Ka by 2 sine theta minus sine theta I, where theta I is the incident angle. So when theta I is 0, then we have normal incidence. So theta I equals 0 degrees is normal incidence. And also we had this intensity equation from here. So what we had was I equals I naught sine beta over beta squared sine n alpha over sine alpha squared. And now minima, previously we saw maxima, but now if you look at minima, then minima occur when alpha is the following. So on and so forth. This is when sine n alpha goes to 0. That's when you see minima. Now from this we find that width of central maximum is 2 pi over n. We will use this later on. So from coming back to this oblique incidence, from here if we differentiate, we get delta alpha equals Ka by 2 cos theta delta theta, and this width of central maximum is my delta alpha. Now I can do some algebra and simplify. So I get delta theta is 2 pi over na cos theta times k, and k is nothing but 2 pi by lambda. Sorry, this into 2. So this is 4 pi over na cos theta 2 pi over lambda. So this gives me 2 lambda over na cos theta. So this gives me delta theta min equals lambda over na cos theta, because I'm looking at the half width. Also, resolving power is defined as follows: R equals lambda over delta lambda min. Lambda is the average wavelength and delta lambda is the difference between the two closely spaced wavelengths which we want to resolve. Now from the grating equation we know that A sine theta equals m lambda. We just saw it in the previous question, this over here. So this means that if I differentiate d theta over d lambda, this is m over a cos theta. So if I combine these two equations and give, instead of d theta over d lambda, I could write delta theta over delta lambda. So now if I combine these two, delta theta divided by delta theta over delta lambda, then I get lambda over na cos theta over m by a cos theta. So a cos theta cancels out. This gives me delta lambda equals lambda over mn. So finally, this implies that r, which is lambda over delta lambda, is nothing but m times n. M is the order, n is the number of lines in the grating. So option C is the correct option. Okay, so let us proceed now. Question number 8. This is also on diffraction gratings. Free spectral range for diffraction grating is what? Please take about a minute to answer. Okay, wait, I think I forgot to restart the poll. Let me restart the poll once. Okay, there you go. Okay, so let us now discuss the answer. So resolving power, as we saw in the previous question, is given as follows. And also we saw the oblique incidence. So we had from oblique incidence so combining these gives me following expression for R. Now when we have two wavelengths, lambda and lambda plus delta lambda, and let us say the lines for these coincide for the orders m and m plus 1, sorry, rather m plus 1 and m. So this means if I use this oblique incidence equation over here, a sine theta minus sine theta I equals m plus 1 lambda, and this line coincides with the line for lambda plus delta lambda, the mth order. So m lambda plus delta lambda. Now if I expand this, I get the following, just simple algebra. This gets cancelled out. And this is known as the free spectral range. Lambda over m. So the correct option is option D. Again, you see that the first two options are dimensionally incorrect because range would have a dimension of length, whereas options A and B have dimension 1 over length. Okay, great. Two more questions to go. Again, a question on resolving power of grating. Resolving power of a grating cannot exceed option A, okay, so take about a few minutes to answer this. Okay, so let us now discuss the answer. Resolving power, as we have seen, is R is equal to lambda over delta lambda min. This is equal to m n. And from the oblique incidence equation, combining this gives us R equals the following. Now sine theta minus sine theta I can take a maximum value equal to 2, and when would that be possible? So when you have sine theta equals 1 and sine theta I equals minus 1. So in this situation you get the maximum value. So what is the maximum value then? Our max is 2na over lambda. So it cannot exceed this. You just cannot get more resolution. If you want to increase your resolution, then as I had mentioned earlier, you have to decrease your wavelength. We had seen in this simple example over here that in order to increase the resolution, you need to decrease your wavelength. So either you could decrease your wavelength or you could increase the number of lines in the grating to increase the resolution. But given a wavelength and a set of lines, this is the maximum resolving power. Again, we see that options A and B are dimensionally incorrect because they have option A has dimensions of length squared, option B has dimension of length, whereas resolving power is dimensionless. Okay, finally the last question for the day. Question number 10. This is on diffraction, Fraunhofer diffraction. Fraunhofer approximation is valid for the following options. Okay, so I will relaunch the poll one last time. Okay, so let us now discuss the answer for the last question of the day. So we need to discuss the basics of Fraunhofer and Fresnel diffraction. So this is my aperture screen. I have some crazy looking aperture, let's say, and here are my axes. These axes are xi and eta, and then I have the screen. Okay, sorry, this is too bad. There is my screen, which is at a certain distance z, and the axis for the screen. Okay, pretty bad drawing. Better. Okay, and this is x and y axis. Now electric field is of the form e to the power ikr by r for a spherical wave, and let's say I'm looking at a point P on the screen and some area element for the aperture, and let's say this distance is r. Then electric field at point P would be the following. A is the amplitude based on the aperture function. D xi d eta is the area element. And C is a constant which we can find out, but we know from the results it is 1 over I lambda. So this gives me the following. And this A is amplitude at z equal to 0. Now what is r? R is, from coordinate geometry, the following. I can take z common out from it, so this will give me z square root 1 plus alpha, where alpha has terms in x and y. Now for very small values of alpha, alpha less than 1, square root 1 plus alpha is approximately 1 plus alpha by 2. So this gives me r is approximately z plus and in the denominator I can replace 1 over r as approximately 1 over z. So this gives me electric field at the point P, X, Y, Z. I can take ikz e to the power ikz out of the integral. It's a constant. Integral over the aperture. I can take this x squared plus y squared term in the exponential out of the integral. So this is the final expression. Now here u is 2 pi x over lambda z, and v is 2 pi y over lambda z in this exponential term over here. Now, this is the case for Fresnel diffraction. This is Fresnel. For Fraunhofer, we replace this particular exponential by 1 for Fraunhofer. And when can we replace this by 1? That means k by 2z is very small meaning much smaller than 1. Then e to the power 0 is 1, so that's why. So rearranging the terms gives us z is greater than k xi squared plus eta squared max over 2. So option A is the correct option. So someone is rightly pointing out in the Zoom chat box that we could have done this by dimensional analysis as well, because options B and C are dimensionally incorrect. On the left hand side we have Z, which has dimension of length, whereas for option B on the right hand side we the dimensions that we have is length cubed, and for C the dimension on the right hand side is 1 over length. Oh sorry, it is dimension less for C, the right hand side, because xi squared is length squared, square root of that is length, and k is 1 over length, so that is dimensionless. And for option B, xi squared is length squared, square of that is length 4, and k is 1 over length, so length cubed. So dimensionally also B and C are incorrect. Okay, good that you have picked up dimensional analysis very nicely. Okay, so this brings us to the end of this week, and one thing I just wanted to show is that I have some simulations for Fraunhofer diffraction. So if you go to this page called Wolfram Demonstrations Project, then I have this demonstration for all of you. It is called Fraunhofer diffraction through a rectangular aperture. So if you click on that, you would see some examples of diffraction through a rectangular aperture. And the parameters that you can change is the length and breadth of the rectangular aperture, the distance between the aperture and the screen, and the wavelength. And you could change these parameters and see the results that are possible. And you could download this. It is free to download, and there is a CDF player which is also free to download, and using that CDF player you can run this Mathematica program. Okay, so coming back, yeah, so thank you very much. See you in the next week. So we are 2/3 done roughly. 12 weeks course, 8 weeks done. Okay, thank you. Bye bye.